All right, hey everyone, welcome to episode 2 of Zero to Hero. I'm here with Maverick, but we'll get to that in just a minute. Um, so as usual, this is brought to you by the NetSec Focus Slack team. There's a link in the description if you want to sign up. I'll be looking along in the live stream channel for any questions that may come up, and I'll pass those along. So a little bit about me. I've been over most of this, so I'll leave the slide up for a second. I'm one of the mods and co-owner at NetSec Focus. It'd be great to see some of you guys out there. But I recently got my OSCP, and the goal of this series is to teach a guy who, Samir, he's not able to make it this week, but I will relay any questions and you guys can be the zeros this week. And if you want to go ahead and introduce yourself.
Sure. So my name is Heath Maverick Adams, and I go by Maverick in the Slack channel. So I enjoy being the dumbest guy in the room, and I find that if I'm not the dumbest guy in the room, it's pretty much time to move on. I had that happen when I was doing help desk, but I do not think that'll ever happen when I'm doing security. So I've been in IT for about 3 years now. I was an accountant and hated every second of it. Don't pick a degree because you think it's safe. Pick something that you enjoy. So I did go back. I got my master's in information systems, and I've kind of just been trekking along, breaking my way into security now. So I've got my OSCP, I've got a CCNA, CEH, which is unfortunate, and a lot of CompTIAs. So right now I'm working as a senior network engineer at a national lab, and I'm also a reserve officer in the Army. So if anybody here is a veteran, thank you for your service. And that's pretty much it.
Cool, man. Glad to have you on.
Thank you.
So this series isn't a super basic series. It's kind of somewhere in the middle for people who have some IT experience or are familiar with some of the concepts listed and are trying to break into offensive security. If you have no idea what we're talking about, check out this link or just Google Apache OCP Prep. He's got a great guide on pretty much everything you need to know. And with that being said, I'm going to switch over the view here, hopefully. And now I am streaming your desktop.
Yep.
So take it away. I'll be muted for most of this, but I'll be looking in the live stream channel on the Slack for any questions.
Okay, sounds good. So in order to follow along today, we're going to cover intro to buffer overflows. You're going to need a Windows machine, preferably Windows 7 or higher. I am running on a 64-bit Windows 10. So if you're running on Windows 10, it's going to make it a little bit easier because your pointer address is going to be identical to mine. You'll also need a Kali Linux machine. You'll need Immunity Debugger and a Mona module for that. And you'll also need a program called Vohland Server. So if we go out to the web here, I've kind of got 3 Google pages going. So the first one is for Vohland Server, and the first link that comes up when you Google it should be this gray corner. If we click on that, when we scroll down to where the comments almost start, you see that there's a vohlandserver.zip here. You just click on that and click here to download the attachment. Go ahead and get that zip downloaded and then unzipped, and it should look something just along the lines of this. So you should just have a basic Vohland server here that will run throughout this demonstration. And then same with the Immunity Debugger. So we have this right here. If we click on this link, and then you have a products page in here. We should be able to go. We're already in the debugger, so we just got to find the download in here. Go see where it's at. Might have to search a little bit harder. Just do a download. So now you have to register. Here's the registration. So you can put whatever you want in here. I I just put fake email and then fake company, and you can put 123 fake street or whatever, and then it gives you a download link, and then it should start your download here. So go ahead and get that installed as well. And then the final thing is going to be the Mona modules here. We're going to need this for one part of our demonstration. If you go to this GitHub, this Corleone here has Mona. And all we need is this mona.py, but you can clone or download this into a zip. Once you do that, we can go into this directory here. So we've got a C, program files, Immunity Inc., Immunity Debugger. That's where it sits. So the only folder you're actually going to need to go into is this py commands. And you're just adding this mona.py module here. So all you're doing is bringing this over and bringing it into this mona.py. So with that being said, I'm going to go over just the basic introduction of what a buffer overflow is, just a conceptual view. So that gives you some time to get these things installed. This is kind of boring, but don't glaze over on me. So if we go into here, and this is also what we'll cover. So we're going to really quickly go over the anatomy of memory and the stack. And then we'll talk about the basic steps of a buffer overflow. So we'll start with fuzzing, and then we'll find an offset. We'll overwrite the EIP. We'll find bad characters. We'll find a module using Mona module. And then we're going to generate shellcode and gain root. So this will make sense here in a minute. Okay, so if we talk about the anatomy of memory, this is kind of what it looks like here from top to bottom. So at the very top, you have the kernel. And the kernel is basically like your command line. And then if you go to the very bottom, you've got text. So text is like your read-only area. And if you want to think of this more in terms of like binary, then you could say that this is 1, 1, 1, 1, and these are all zeros down here. So, and then this is everything in between. So when we look at a buffer overflow, really we're talking about the stack. And when we look at the stack's going to grow downwards, and then the heap should grow upwards. And if we go into the stack and we look at it here, this is really where the buffer overflow starts. So again, if we're thinking about things here, we have the top of the stack, which is our ESP, and then we have the bottom down here, which is the EBP. So when you want to think about the bottom of the stack or the base, you just think of a B here for base, and then you should know you're at the bottom. So what we're concerned with is buffer space right in here. When we have buffer space, in theory, we're supposed to have sanitation when bytes are sent into this buffer space. And if you have proper sanitation, you can fill up this buffer space up into this EBP point. So in theory, everything should stop. Now, if you have a buffer overflow, then you overflow this entire point and you get down to this EIP, which is a pointer, and you can start to get malicious. So with this, we can control this EIP. If we're able to overflow it, we can control it, set a malicious return address, point that to some malicious code, and then get a reverse shell and have root on a machine. So that's going to be our overall goal today. So what we're going to start with is we're going to start with fuzzing. And when we say fuzzing, we're going to send X amount of bytes. We'll start with 1, and then we'll just keep going with 100. We'll do 300 onwards, all the way down. And we're going to try to cross over. So in theory, if we were to have good sanitation, we should send endless bytes and nothing would ever happen. But that's not what's going to happen today. So we're going to send bytes down, and we're eventually going to overwrite the EIP. Once we do that, we need to find out at the exact point that we're going to do that. So that's where we're going to start to find our offset, and we'll continue on from there. So let's go ahead and go right into fuzzing. So I'm going to bring up my Kali machine here first. And I've already got some scripts written out just to make this a little bit easier. So for step 1, let's look at our fuzzing. So this is a script that I have. It's a Python script, and we can go over it really quick. So we're importing socket, we're importing sys, and then we're going to define here a variable just called buffer with a. So a's are going to be represented in bytes by x41. And what we're going to do is we're going to set a counter of 100, and then we're going to run a while statement here. And we're going to say, while the length of buffer is less than 30, then we're going to keep doing this. We're going to keep appending to this counter. So what this means is we're going to send 30 iterations of this counter. So we're going to start at 100, and then we're going to go up to 300, then 500, and I believe at 30 iterations, we end somewhere at 5,900. So when we're doing that, as long as that's looping, then we're also going to send that to our Vohland server here. And I'll show you what some of this means in a second. So I just put in a print statement, and we have a S variable just saying to connect to the socket. AF inet is IPv4, and then your sock stream is your port. So we're doing a connect. This is my IP address of the machine that's going to be running the Vohland server here. So this should be your Windows 10 IP address or your Windows 7 IP address. And then the default port, unless otherwise instructed for it, is actually 9999. So we're going to send a message here, which is this trun message. And this is just standard. You're going to have to copy this from me. But this is just a standard overflow here. I can show you where we're pulling this from. If we actually load up our Vohland server and make sure we run it as admin.
Maverick, when you get a second, can you increase the font size on your terminal?
Yes.
Awesome, thanks.
Okay, so we've got a connection here with Vohland server. I've got that loaded up. And what we're going to do is we just can netcat to it now. So we're going to keep the same IP address structure, this 192.168.15.102, and we'll just netcat out to 9999. Okay, and you can see we made a connection here. We just type in help. And so Vohland server has a variety of different vulnerable lines and values in here. So where we're pulling this truncate is just right here. So that's where this command's coming from. So that doesn't seem strange that we're just saying that. So if we go back to the code. So now we're going to send that message, and then we're going to send our string. So our string is going to be the value of these A's in increments. So we're going to send 100, then 300, then 500, and then we're going to close it out. At some point, we should see that our program will crash. In some instances, Python will actually stop in the area where the bytes actually overflowed the program. But in this case, it's not going to happen. So we're actually going to go through our whole iteration. But what we're looking for is some sort of crash in the program. So let's go ahead and I'm going to control X out of this. What we're going to do is we're going to load up Immunity Debugger and make sure we run it as administrator. And we want to attach Vohland server here. So if you come into File, Attach, and Vohland server is the first one. If you have any trouble finding it, just sort by name. Then we hit Attach here. And then it's critical that we hit play or start so that it says running down in the bottom. So what we're going to do is we're going to come back into our Kali machine, and we're just going to fire off this 1.py or fuzzing. So now what's happened? So we violated the program when executing. And like I said, we were sending a bunch of A's, so 41s in bytes, and we've basically caused the program to malfunction. So you can see here that we sent that trun message with a bunch of A's. It came across, we went through over the ESP, we went through the base, the EBP, and then we actually made it all the way down to the EIP. So our goal was to overwrite the EIP with 41s, and that's exactly what we did. So step 1 is good to go. So what we actually need to do now is we need to find exactly where this EIP area is. And to do that, there's actually a tool called pattern create and pattern offset that we can use. So if we go back into Kali machine now, and we can just do a locate on it. So this is the location. It should be the same if you're running Kali. The user share, Metasploit framework, tools, exploit, pattern create. It's a Ruby. So we'll just paste that. And we're going to set a length. So switch of L and 5900. So what we did was we know that somewhere between 1 byte and 5900 bytes that we overwrote the EIP, but we're not exactly sure where that happened. So what we're going to do then is we're going to generate a pattern here that's unique, and we're going to generate it at a length of 5900 bytes. And then instead of sending out, a bunch of A's in like this and fuzzing it, we're going to send this whole 5900 bytes, and we're going to see what the value of the EIP is at that point. So then we can come back and we can look for the pattern offset and find exactly where that offsets. So let's go ahead and just generate this. Okay, so you should get a bunch of text here, 5900 bytes. And then all you'll want to do is grab this and we're going to copy it. So again, just for ease here, I've gone ahead and created a script, and I will walk you through the adjustments that we made. So I created a shellcode here, or shellcode variable, and I pasted in this offset. And originally we had buffer here, the counter, the wall statement. You could take all of that out. And then you can also take out your for statement. And then we just want to leave this s.connect here, the socket. Want to leave that outside of our try statement. So now what we're going to do is we're going to put in a try statement, and we're going to say try connecting to this IP at this port, and then send this message with this shellcode. So if it doesn't work, we're going to hit an exception, and it's going to tell us to go ahead and check the debugger. So what we'll do is we'll shoot this off again. What we need to do is actually, I recommend closing out of Immunity Debugger. I get errors when I try to detach and reattach. So my recommendation is just to rerun everything. So rerun it as administrator. Make sure you also rerun your Vohland Server as administrator. And let's come back in here now and let's attach this. So same step here. What we're going to do is just hit the play button. Make sure it's running in the background down here. We'll close out of this code and we'll just execute it. Okay. And now if we come in here, you should see your Immunity Debugger it should be blinking if something happens. That's usually a good sign. So we've hit pause status again. We had another violation. And now you can see that it sent that truncate message again, but it just sent all this random gibberish that we told it to send. So this is our randomly generated code. And then now we see the EIP is actually sitting at 386, looks like Foxtrot 4337. So what we can do with that information is now we can type in these 8 bytes here and see if there's an offset. So if we tab up just a couple, you can pretty much keep the same syntax. What we're looking for is offset here. And then we just need to enter in the value we found. So we're going to keep the length. And then we're going to enter in a switch of Q. And we're going to type in 386 Foxtrot 4337. And let's see if we can find our location here. Perfect. So this is good news. If you were looking for something and it wasn't there, like let's make this a 6, it should tell you, unless there is this pattern in there for some reason. So no exact candidate here, but it's looking around and it says, hey, we might have found one in 2003. Maybe we had a typo here. So it's kind of smart in that sense, but you're looking for an exact match. And our exact match is going to be at 2003. So what that means is the EIP starts at the 2004th byte. And we can look at that in code. So I'm going to show you my next set of code. And from here, nothing really changes that much. So instead of the shell code being that random generated 5,900 bytes, now all we have to do here is we can just send out an A times 2003 and then a B of 4. So what we're doing is we want to see and confirm for our own sake that we can overwrite the EIP with 4 Bs. So once we know that we can overwrite it, then we have full control of the EIP, we can find a good module, and then we can send our malicious code. So we just want confirmation that we can do that. So let's go ahead and try that now. I'm going to close out of Immunity Debugger and get everything reopened one more time. Okay, we'll hit the play button. We're running down the bottom again. Let's close out of this. Okay, let's see what happened. Okay, so we paused again, another violation, and Bs are represented as 42, 42, 42. So we've got 4 Bs here, and we have successfully overwritten our EIP. We're now controlling our EIP, which is really good news. So our next step that we need to do is we need to start looking for bad characters that won't be well represented in this code. So in certain code, in certain programs, when you send out a bad character, it could cause something to happen to where we can't send out the right exploit. So for example, a X00 byte will completely truncate wherever it lands, and it will just mess up your exploit. So there are other characters that might do similar things. So we can actually send out a bunch of bad characters to see if we can find that as well. So this will be a better example once I can show you. So I'm going to go ahead and close out of this again. And I want to show you the code. So if we go into the next one here. So what I have is we still have the same line of shell code with the A and the B. All we're adding is a variable now in of bad chars. And it's just a bad character list. So it goes through X01 all the way down to, I believe, XFF. Right, so we're down here at XFF. And if you want to find where to generate this, you can actually grab this somewhere. If you want to look on Google, you can grab it. We can just go out to Google and say bad characters, Python, and look for a list. If you look around, you should be able to find something in here that will give you this list. If not, if you want to message me, I'm happy to send it to you as well. Or if you want to take the long way, which is what I did, is you can just type it out. So X01 through XFF. And then we're going to do the exact same thing where we send this. And then there will be a way we can inspect to see what bad characters are not there. So I'm going to go ahead and prep this to send. I'm going to get Immunity Debugger loaded one more time. Okay, so let's go ahead now and let's send this. So another pause here. And what we're going to be looking for is if we click on this ESP right here, so the top of our stack, and we go down and we click on follow in dump, it's going to take you right to these characters that we just sent over. Let me see if I can make this any bigger for you guys. It looks like it's as big as it's going to get. So I'm going to pull up a picture for you as well. So what you want to do is you want to look at this and you kind of want to go through your list. So you started at 1. So you're going to go 1, 2, 3, 4, 5, 6, 7, 8. And you're just going to go all the way across until you get down to the bottom where you had FF. So I'm going to go ahead and save some time and tell you that there's no bad characters in here besides zeros. But I do want to show you a picture of what bad characters look like. That way you just kind of have an idea. So this is another example of something I've worked on that had bad characters. Let me zoom in on this. So you can see pretty much right away, if we're coming through here, we got 1, 2, 3. Okay, this should say 04, but it says B0. This should say B0. So we know immediately that 04 and 05 are bad characters. And what you want to do is you want to continue to go through this list until you find all the B0s that are in here. And you're going to take those out when you generate your shellcode. So you're going to write these down somewhere, make note of them, and keep them for when you're generating your shellcode, or else your shellcode is just not going to work. So it's kind of a tedious process, but you got to pay attention and make sure you catch all these, because it's kind of a pain to go back through when you miss just one of them. But lucky for us, we don't have to go through this whole thing. I'm telling you that there's nothing in here that's going to be a bad character. So this is a pretty straightforward exploit. So what we need to do now is we need to go and we need to find the right module. So what that means is we need to find a module that has no protection, such as DEP or ASLR. And to clarify, DEP is technology that prevents malicious code from running on systems. ASLR is address space layout randomization. So what it means is it's randomizing the base address of an application that every time the OS is booted. So we need to make sure these protections aren't set on there, or it makes it way more difficult for us to generate shellcode and get root. So we're going to look through modules, and we're going to look for false statements, and we're going to look for a DLL file that we can attack. So in order to do that, we're going to come in here, and I'm going to kill everything one more time and get it loaded one more time. Okay, so let's attach this. And down here at the bottom, you should be able to enter in some line of code here. So we can actually put an exclamation in there. We're going to say Mona modules. So this is where I had you go out and download the Mona module, because it doesn't come standard with Immunity Debugger. So what we're looking for is, like I said, no DEP, no ASLR, and also no bad characters. So if we were to see, if we had bad characters, the zeros are okay here, but if we had bad characters and we saw them in this, we wouldn't want to use it. So if we look straight across, the first thing I kind of like to look for is just falses across the board. So we see falses across the board here, and we see falses across the board here. Preferably, this is the executable. So really, we want to look for the DLL. And the DLL is right here. So the ESS func DLL, and we can see that this is actually running as part of Vohland Server. No ASLR, No other protections sitting under here. So this is something that I would call good to go. So now that we know it meets the criteria, what we need to find is something called the opcode equivalent. And we're going to be looking for a JMP ESP. So what we're doing here is we're trying to find a jump code in order to jump to this module. So what we're going to do is we're going to use something called NASM shell, which is going to convert assembly language into hex code for us. So we're going to convert this JMP ESP into hex code, which should always be the same thing. It's going to be FFE4, but I'm going to show you how to do that here. So if we go back into our Kali machine, what we're looking for is this NASM shell. Okay, so again, we can just copy this. And just run it as is. Might take a second to bring up the module. And then what we're looking for is JMP ESP. You hit enter. And like I said, it's bringing up FFE4. So that's our opcode equivalent. So what we're going to do with that is we're going to search for that opcode equivalent in our DLL file. And that should give us some sort of return address to point back to. So let's go back into Immunity Debugger. And from here, we can keep the Mona. We can delete the modules here. But we're going to say find. We're going to do a switch of S. We're going to do quotations here. So quotations. And then we're going to say XFF XE4. So that's the FFE4 and the quotations. Going to do a switch of M, and we're going to call out this ESS func.dll. Okay, so it gives you a bunch of results down here, and this may be hard to see, but what I like to do is I like to just pull the first return address I see, and if it doesn't work, I like to kind of go down the list. So the first return address we have here is a 625011AF. So what we can do here is we can put that into our code. Let me show you how that'll work. Okay, so the code that we got originally was, it looks something like this. It was 625011AF. So if you can see, I have it in here, 6205, this says 50, it's backwards, 11FA, AF, right? So what we're going to do now is we're putting it backwards because of the architecture. And when it's backwards like this, it's called Little Endian. So because it's an x86 or we're a 32-bit architecture, we're storing addresses in this Little Endian format. So the lower order byte is actually stored at the lowest address, and the higher order byte is stored at the higher address. So that's why we're putting this in backwards. So now what you can tell is we kept the A's, but we're replacing the B's. So the B's were just a placeholder on our EIP. Now what we can do is we can actually point to something. So we're pointing somewhere else that we can execute our malicious code. So we're pointing to that DLL now. And then once we can successfully point to that DLL, all we have to do is enter in malicious code and we should be good to go. So there's a couple things we need to do here to test to see if this works. So let's go ahead and get our Immunity Debugger back up. I'm going to close this out one more time. And then we shouldn't have to close anything here. Let's just let it run. Everything should be good to go because we haven't pushed any code. So what we want to do is there's this little bluish, blackish arrow here. If you click on that, we actually want to try to follow this expression. So when it says that, we're going to search for this 625.0.11 AF. Let's try it one more time. Okay, so you might have to do it a couple times. So 625.0.11 AF, it's FFE4, and it points to this JMP ESP. This is exactly everything we want here. So what we can do is we can set a breakpoint. So a breakpoint is just going to tell the application to stop if it receives something at this point. And so we want to point to this address, but we don't want to go any further, and there's nowhere that we're pushing further at this point. So what we can do to set a breakpoint is just hit F2. It should highlight blue like this. And then we're going to make sure everything's running. And we can execute this new code that we just did. Let's give it a try. Okay, so now it's paused. And instead of a violation, you actually see breakpoint at ESS func, and then it gives us a return address. So what that means is we were successfully able to hit this breakpoint. So now we've got a new pointer. All we have to do now is enter malicious code in, and we're home free. So we're going to generate some malicious code with MSF Venom. And let's go right back into our Kali machine. I'm going to walk you through this. So I'm going to do an ifconfig. I just want to know my IP address. So I'm sitting at 134.130 or 141 here. So the syntax we're going to use, it's going to be MSF Venom. And I'm going to use a switch of P for payload. Since we're on a Windows machine, I'm going to use Windows shell reverse TCP. I'm going to do a non-staged payload here. And my L host, which is going to be us, our Kali machine, our attacking machine. So we're going to use the IP address we just found. And we're going to have an L port of 4444. That's the standard default one I use unless I run into any sort of errors with that. We're going to do an exit function of thread. This is just going to make our shellcode a little bit more secure. We're going to do a file type of C. We're going to do architecture of x86 because we are doing 32-bit. We're going to do a 2 hyphens platform Windows. And then the switch of B. Here's where your bad characters come into play. So we're going to do x00 because that's the only bad character we knew. If there were more, you can add them in. Remember, we saw the one that was x04, x05. But in this case, we just have 00. So we run this. And it should generate some shellcode for us. And this is kind of what it looks like. So it's 351 bytes. And what we're going to do is we would just copy this here. And then we have our final code, which should be the same. Nothing should have changed since I've run this. And this is kind of what it looks like. So we're calling a new variable here called exploit. And this is where you put in the shellcode that you just generated. And all this shellcode is doing is telling your computer to talk back to our computer, or the victim computer to talk back to our computer. So it's going to be a reverse shell because we're going to make the victim connect to us here. So same concept. We've got our 2003 A's. We've got our new pointer that we found to be good by setting the breakpoint. I've added in this exploit back over here, and then I just added in some of these X90s. So these are NOPs, or they stand for no operation. All you need to think about these are, you need to think about them as padding. So if we were to put our exploit here and we were to have no padding at all, it's possible that the shellcode is going to interfere with the return address. So we just want to give there some room in between. So if our return address and our exploit have a little bit of padding in between them, should be good to go. So I'm going to put just 32 NOPs here of padding, and the rest is going to stay the same. So we're going to go through, connect to the same IP, connect to the same port, and hopefully we get a reverse shell. So I'm going to Control X out of here. I'm going to close out of Immunity Debugger. We're not going to need that anymore. And I am going to run Vohland Server one more time as admin. So we need to do a couple things here. Before we send this off, we're going to go ahead and put a netcat. So we're going to set up a listener here. So let's just do a netcat MVLP, and we're going to be listening on 4444. So if we send this off, in theory, our victim should connect back to us. Let's see what happens. And there we go. So now I am sitting on this computer. I can do a who am I. It's going to be under my name here, Heath. But this is an admin user. So for all intents and purposes, I have full rights to this machine. I can do whatever I want, and I'm in full control. So that is it from start to finish. We just went over everything. Remember, we started with fuzzing. We made sure that we could overwrite to the EIP. So once we figured out the EIP that was vulnerable to buffer overflow, then we were able to create a unique pattern. And we used that unique pattern to find an offset. So once we found our offset, we were able to go ahead and test it out. We overwrote the EIP with our 4 Bs and went from there. We were good to go, so we decided that we were going to look at bad characters. We found no bad characters besides zeros. So then we just started looking at modules. We wanted to find what a good module was so we could find a good return address. So remember, we looked at the Mona modules. We went through them. We found things that didn't have anything with DEP or ASLR or safe SEH. And we found the ESS func module. So when we found that module, we just needed to find the opcode equivalent of JMP ESP and then search for that back again in the Mona modules. So we were able to find the JMP ESP, the XFF XE4, if you recall correctly. We were able to find a good return address. We were able to enter that return address in and hit our breakpoint when we set one. And then finally, we were able to generate a shell code, talk to that pointer, point back to this malicious code, and we were able to get root on our machine. And that's it from my lesson.
Awesome job, man. Can you hear me?
Thank you. Yep.
Awesome. Well done.
Thank you.
Well, that's about it for this episode. Thanks again for coming on. I'd love to have you on in the future.
I appreciate it. I'd love to be back.
Awesome. And with that, I'm going to end the stream.